Okay, hi guys, good morning. Start. Hope all of you are there. Most of you are there. We'll start right away. I'm gonna share my screen. Okay, so you hope you're able to see my screen. Right. So yeah, so hope you remember what not we saw last class, right? So let me just quickly recap of whatever we saw, right? So we started with the relationship between Kc and Kp. I think let me see if I have right. Do I have? Okay, no issues, right? So let me add a page and let me see what and all I saw. Right. So we saw the relationship between Kc and Kp. Can someone tell me what was the relationship between Kc and Kp?
Kp equal to Kc
Hmm.
RT raised to the power delta n.
Right. So I have this equation Kp. So I have basically Kp to be equal to Kc RT the whole mean only for RT the power is there RT power delta n, right? So what does this delta n specifies?
Total stoichiometric coefficients of the product minus total stoichiometric coefficient of reactants.
Exactly, right? So this is basically going to be you have to add all the stoichiometric coefficient of products and you have to when you have to add all the stoichiometric coefficient of reactants and then subtract them both, right? So this is the relationship we saw for Kp and Kc together, right? And then we went on to see what are all the properties, right? What are all the properties of the equilibrium constant? And I told you that the equilibrium constant Kc or Kp for that matter is independent of the initial concentration, right? No, it doesn't matter how much you start with, right? That value is going to be constant. But my Kc and Kc and Kp are going to be temperature dependent, is it not? Right? So you definitely now I even have an equation connecting temperature and equilibrium constant, but that's not there in your syllabus, right? But Kc or Kp will vary with temperature. At one constant temperature, they are constant, right? And then we went on to see what are all the operations I can do on your Kc or Kp, right? So now tell me, okay, let me ask someone. Maybe, okay. Shruti, are you there, Kana?
Yes, sir.
Kana, can you tell me any one? I basically have three operations which I can do on equilibrium constant. Can you tell me any one of them?
Like the formula, sir?
Yeah, so like for example, what happens if I add two reactions? What happens if I reverse the reaction? What happens when I multiply throughout the reaction by a factor of n? So these are three operations I can do. So if I do that, I can tell any of them what will happen to the Kc. Say for example, I'll take A giving B is a reaction, right? Say for this it is Kc. For B giving A, what will be Kc dash in terms of this Kc?
In the first one, it will be concentration of A.
So the K,
Concentration of B by to the power B by concentration of A to the power A.
no, here I don't have any A and B. All the stoichiometric coefficients are 1 only. So no issues. Okay, fine. So this will be B by A. Okay, right? Fine. So for this, it will be.
A by B.
So what is the relationship between between Kc and Kc dash?
It is Kc to the power n. Kc dash is equal to Kc to the power n. Concentration.
How? Now look at this. Kc is B by A. Kc dash is A by B. So what is the relationship?
It's a reverse of each other.
Reciprocal, right? So then the perfect term you have to use is reciprocal. So this is the first operation, people, right? So whenever you reverse a reaction, the equilibrium constant of the first reaction will become the reciprocal of the second reaction. So Kc dash in this case will become, not only in this case, any case where you reverse a reaction will become the reciprocal. So Kc dash will be equal to 1 by Kc, right? Okay. So maybe I'll ask someone else now. Okay. Venisha, either kana, maybe in the chat. I think she's available in the chat. Okay, Venisha. So Venisha, when I multiply throughout a reaction by a factor of n, what will happen to the Kc? Say I have A giving B is a reaction. Now I have, say, Na giving Nb. What will be what is the relation between the two reactions in the sense in terms of Kc? Hope you're writing something or you're thinking. Yes, when do you know the answer? Or I think she's typing. Let me give her some 10 seconds. Okay. Fine. So maybe if the question was a problem, say if this is the reaction and I have Kc for this, if I have, say, Na gives Nb, say for this it's Kc dash, what is the relation between Kc dash and Kc is what I'm asking. Say for this.
Kc to the power n.
Correct, right? So it will be Kc power n. So remember, whenever you multiply throughout the reaction by a factor of n, the equilibrium constant is gonna raised to that power. So it will be Kc power n. So for the first reaction, it's Kc. Now I have multiplied by a factor of n, it becomes Kc power n. Right? Okay, this is the second operation. And the last and final operation is when I add or subtract two reactions. So when I add two reactions, what should I do to the two equilibrium constants? Anybody can answer. Say if I have A giving B is K1, B giving C is K2. Say if I have A giving C, say this is K. What is the relation between K, K1 and K2?
So it is
K equal to K1 into K2.
Yeah, right. So whenever you add two reactions, you should not directly add the equilibrium constants. Rather, you have to multiply it, right? So if you remember, you can see A giving C. How is it going to come? If I add these two reactions, A giving B and B giving C, if I add, I'm going to get A giving C. and the equilibrium constant K will be equal to K1 into K2. Right? We even proved it last class. You can just look into your notes if you have any doubts, right? So in this case, the third reaction will be equal to, equilibrium constant is equal to K1 into K2, the first two equilibrium constants products, right? Okay, so these three are the operations and you have to remember this. So one is reversal of the reaction, multiplying throughout by the reaction by a factor of n, and third one is addition or subtraction of two reactions, right? So these are all the operations and properties of the equilibrium constant, right? Then I told you that when you have say both reactants as well as product initially at time t is equal to 0, you don't know which side the reaction will proceed, either in the forward direction or in the backward direction. And there was one term which was going to help us, and what was that? For deciding whether it is going to move forward or backward, if I have both reactants and products initially itself, what is this term which is going to help us find out which side the reaction is going to happen? What is the term called as?
That reaction quotient.
Yeah,
Right?
yes, it's called a reaction quotient, right? So reaction quotient is denoted by the letter Q, right? Hope you remember. And this has exactly same formula as the equilibrium constant, right? But what is the difference? This is also going to be products divided by reactants, concentration of products by concentration of reactants only. But again, powers, obviously, if I have stoichiometric coefficients, right? So what is the difference?
This is for initial, sir, while Kc is for final.
Okay.
When it reaches equilibrium, we use Kc.
Understood. Yes, correct. Right. So this, what is that? This reaction quotient, the concentration values you are putting here, right? They need not be any initial. There can be any concentration for that matter. Any concentration in the starting, in the middle, in the end, whatever it is. Accordingly, you will put the concentration. This concentration can be at any point of time, right? But for Kc, it is fixed. It is fixed at equilibrium. At equilibrium, at the end of the reaction, what concentrations do you see? Those concentrations only you have to substitute for Kc. But for Qc or Qp, it doesn't matter. You can substitute anytime. And obviously, if you want to check whether the reaction is going to move forward or backward, you will put the initial concentrations here: initial product concentration, initial reactant concentration, right? And now, obviously, how will I predict now? I have to go for comparing the value of Qc with Kc, right? So there are three cases, right? So I hope you remember, and we proved it also, and I hope you remember the logical explanations for this. Maybe that page is there. I can show you. Yeah, this is the page, right? So if you can look at it, the first condition, right, is Qc is equal to Kc, right? So Qc equal to Kc, that means what? The equilibrium has been reached. The Qc value, the concentration value substituted for Qc are going to be equilibrium concentrations. So obviously that means that the reaction has reached equilibrium, right? Now, say the second case is that when you find that the Qc value is less than the Kc value, right? So now, as I told you, eventually you want to reach equilibrium, right? So what you have to do to the Kc, if you want to reach equilibrium, the Qc has to become equal to Kc. So obviously now this time I see that the Qc value is lesser than Kc. So I have to increase the value of Qc. So now how will I do it? Obviously the product concentration has to be increased, the reactant concentration has to be decreased, and that will happen eventually on and only if I have forward reaction happening, right? So right. Same way, the third case is that when I have QC less than KC, right? Now again, I have to reach equilibrium. And if I want to reach equilibrium, I have to make sure that the QC value decreases, right? How can I decrease the QC value? The same formula only. So I have to decrease the concentration of product, increase the concentration of reactant. So obviously that will happen only if I have backward reaction happening, right? Okay. So these are all the things we saw last class. Okay, so we'll continue, right? I think today I can take you to little bit of problem solving and little something else. So we'll see. Right. Okay. Fine. So how do you approach problems, right? So please understand, people. When I go for the problems point of view, right? So any problem in this equilibrium chapter can be divided into two cases, right? So one is that where I have delta n is equal to 0 kind of reactions. Another case where I have delta n not equal to 0 kind of reactions. Okay. Now what we know what is this delta n? This is not E, people. This is 0. Okay, right? So the delta n equal to 0 kind of reactions and delta n not equal to 0. Hope you understand what I mean by delta n equal to 0 kind of reaction. That means the stoichiometric coefficient of reactants and the stoichiometric coefficient of products are same, right? Only then if you subtract the total stoichiometric coefficient of products minus total stoichiometric coefficient of reactants will become 0. Only when I have both the stoichiometric coefficient to be equal. Say one of the reaction can be like this. Say I have H2 plus I2 giving 2HI. Right? Now what happened here? The total stoichiometric coefficient of product side is 2 and total stoichiometric coefficient of reactant side is 1. I mean 1 plus 1 becomes again 2. So delta n is equal to 0 for this kind of reactions. Right? Say, but if I have reactions like say PCl5 giving PCl3 plus what happened? I have 2. In the reactant side, I have only 1. So definitely 2 minus 1 will become 1, which is not equal to 0. So hope you understand what you mean by delta n equal to 0 and delta n not equal to 0. Okay. So what I'm trying to tell you is problems with the delta n equal to 0 are actually of little easy problem solving. But when it comes to what is it, delta n not equal to 0, it's not like it's difficult. But yeah, I'll tell you what is the basic difference here. Okay, so let me take a reaction where delta n is equal to 0. That means let me take this reaction itself, H2 plus I2 giving 2HI. I assume that I have this reaction only, right? So now what I do is, let me do it in terms of concentrations. Okay, so now if I write the Kc value or Kp value, Kc value I write. So how will I write? It will be concentration of Hi squared divided by concentration of H2 into concentration of I2, right? So basically this concentration what we are using here is going to be molarity, and we know what is the formula for molarity. Molarity formula is number of moles by volume. Okay, so now if I get that also into the picture, right? So what you have basically number of moles of Hi divided by the volume whole squared, right, divided by number of moles of H2 divided by volume. See, now why am I putting the same volume here? Because everything happens in the same vessel. Say it can be a 5-liter vessel, it can be a 2-liter vessel. The vessel is same, right? In a Hi, H2, Hi, everything is in the same vessel. So all of them will have same volume only. Okay, so number of moles of H2 by volume, and at last I have number of moles of I2 divided by volume. Okay, now what you see here is that the volume terms are going to get cancelled, isn't it? I have numerator v squared, again denominator also I have v squared. So all these v's gets cancelled. So what is remaining? I basically have number of moles directly. So what I see here is that instead of using the concentrations, we can actually directly use your number of moles itself. That's what I'm telling. So what will be number of moles of Hi squared divided by number of moles of H2 into number of moles of I2. So basically, instead of doing it in terms of concentration, for delta n is equal to 0 kind of reactions, you can directly use the number of moles. There is no need to use concentration. Even if you use concentration, doesn't matter. You're going to get the same answer, but just that one step will be little less. Okay, so because all the volumes are getting cancelled, not only for this reaction, any reaction where you have delta N equal to 0, definitely all the volume terms will get cancelled and you can directly use the number of moles in the Kc or Kp equation. I mean, not Kp equation, obviously, Kc equation. Right? Okay. Now, definitely, I will not be able to do that for a delta N not equal to 0 kind of reaction. Okay, right? Because obviously one of the volume term is going to be there. So it's wise to use directly the concentrations rather than using number of moles. Okay, right? So this small point I wanted to tell you. Right? Now, how will you approach problems? Right? Let me do that. Right? So, like if you can make one simple thing, people, right? So for any problem for that matter, right? If you can draw this something called as equilibrium table, if you can do this properly, right? If you can make the equilibrium table properly for any given question, right? Your 90% problem is solved there only. Okay, now what do you mean by equilibrium table? Very, very simple. Okay, let me take an example and explain you. Okay, say I have, let me take okay, let me take few examples then, not only one example. Let me take your HI example itself, right? Say I'll take the reverse reaction this time. Say it's 2HI, right? Say 2HI gives H2 plus I2. Okay, fine. I have this reaction with me, right? Or let me take an easier example for now. This is also an easy example, but 2 and all comes. I don't want any stoichiometric coefficients. Let me take PCl5 example. That's a good example. Okay, so I have PCl5 giving PCl3 plus Cl2. Okay, now this reaction they have given to me, right? So the question says like this. Initially, say now what you have to do is you're gonna look at the time periods. Now initially at time t is equal to 0. Now obviously they would have given some condition, right? The conditions would have been initially I had 5 moles, right? 5 moles of PCl5. Say I write it. I have 5 moles of P5 in a 1 liter vessel. Okay, so this condition is given to you, right? So they are given initially, I have 5 moles of PCl5 in a 1 liter vessel. Okay, right? Now I say that at equilibrium, right? At equilibrium, say 60% of reaction is completed. 60% reaction is completed. Okay, so these two are the thing, information given to you. So they initially they say that I have 5 moles of PCl5 in a 1 liter vessel, and they say that in equilibrium, the 60% of reaction is completed. Say they ask you what is the concentration? What is the concentration of PCl5? So let me ask you the question directly itself. So I want to know what is the concentration of PCl5, PCl3 and Cl2 at equilibrium. So when I reach equilibrium, I want to know, right, what is the concentration of PCl5, PCl3 and Cl2, and you have to also find the Kc value also. Kc value also you have to find. Right? Or directly I can ask you to find instead of I can just ask one question. The one question is what is the Kc value? That question is sufficient because that anyways includes calculation of other stuff also. So again I repeat the question. So they say that at initially 5 moles of PCl5 was there in a vessel and the volume of the vessel is 1 liter. right? So they say that at equilibrium, 60% of reaction is completed. That means what? Obviously, 60% of the reactants has converted to products. The reactions come to an end. That's it, right? That 60% only is completing. That's it, right? They're asking, what is the Kc value? Okay, right? Now, pretty simple. As I told you, when you can make this something called as equilibrium table properly, your 90% job is done, right? So what do you mean by equilibrium table? Let me drop this t is equal to 0. Right. So at time t is equal to 0, right? You just have to fill what is given to you, right? So initially, how much of so you're talking in terms of number of moles now, right? So like you can just put t is equal to 0 here. You can even put n, right? So when you put n represents number of moles. If you put say m represents molarity. So how whatever data you want to put, you can put in whatever way you want to put it. Okay, so here using number of moles. Like it's better to use number of moles always, and then you convert it into molarity. Okay, so number of moles of initially PCl5 is 5. It's given in the question, and they didn't give you any information about Cl2 or PCl3. So obviously they're going to be 0. There is nothing initially, right? So now what they're telling, now at times sometime at equilibrium, right? At equilibrium, what happened? This 5 is not there. Some X would have reacted, correct? Some X moles of PCl5 I will actually find out this X, don't worry. Okay, so I said that some X moles would have reacted. Okay, now how much would have been here? Tell me how much amount of PCl3 and how much amount of Cl2 would have been there? I have initially 5 moles of PCl5. Out of that, at equilibrium, X moles have reacted. How many moles of PCl3 and how many moles of how many moles of Cl2 are there at equilibrium?
Is it like 60%?
Yeah. So what is the what? So if it in terms of X, how will you write here? Now look at the stoichiometry, people. I have 1 mole of PCl5. If it reacts, I'm getting 1 mole of PCl3 and 1 mole of Cl2. So how many moles of PCl5 are reacting here?
5 moles.
No. 5 moles are initially there. How much is reacting?
60%, sir.
Forget about the data. Look at this table and tell me how much is reacting.
5 minus X.
Only X is reacting, right? Out of 5 moles, only X is reacting. Do you understand what I'm telling? Right? I'm asking you how much of PCl5 is reacting. Initially, I had 5 moles. Yes. Right? In that, how much has been consumed or how much has reacted is basically this X moles. Right? How much is remaining? Obviously, remaining is 5 minus X. How much of PCl5 is left unreacted? That is 5 minus X. Completely true. Right. Okay. Now tell me, 1 mole of PCl5 gives 1 mole of this and 1 mole of this. So now I found out that X moles are reacting. So how many moles of PCl3 and how many moles of Cl2?
X moles, sir.
Right. Exactly. It's X moles. 1 mole gives 1 mole, 1 mole. So X moles will give X moles and X moles of this. Right. And that's it. Now I know how much is this X. I actually in the question X is given to me. What is X? Can you tell me? Okay, so basically they're telling that 60% of reaction is completed. That means 60% of 5 moles of PCl5. Oh wait. Has reacted. Right? So that's what is given in the question. They say that at equilibrium, 60% of reaction has been completed. That means initially I had 5 moles. Out of this 5 moles, 60% of them would have been converted to products. Right? So obviously, what is 60% of 5?
3, sir.
Right, you can calculate using the formula or logic. 60% of 5 is basically going to be 3. right? So what now you can easily find the X value. That is what is getting converted, isn't it? 50%, 60% of 60% of this thing, PCL5 is converted to the products, right? So this X is basically going to be 3. 1 second, guys. Right? So this X is basically going to be 3. Correct? Right? So what, now if this is 3, if this X is 3, obviously this X is also 3 and this X is also 3. Done. Right? So now what I have to find? They have to find the Kc value. So these are the number of moles. So 5 minus 3, 3 and 3 are the number of moles, right? Now what I have to do is I have to find the concentration. So obviously number of moles by volume is what is the concentration. But in this question, they have made things easier. They have given that it is going to be 1 liter vessel, right? So all this divided by 1, X divided by 1, X divided by 1 would have been the concentration. So anyways, now you don't have to worry about it. Now you can easily find the Kc value, right? So Kc value, you can easily find, right? So always remember you have to use the equilibrium concentrations, right? So equilibrium concentrations are basically it will be concentration of PCl3 into concentration of Cl2. What is concentration of PCl3? 3 by 1. What is concentration of Cl2? Right? So concentration of Cl2 is also 3, right? Divided by what is concentration of PCl5? PCl5 is 5 minus 3. What is remaining? Obviously, after the reaction, that is 2. That's it. So it will be 9 by 2, which will be 4.5. That would have been the answer, right? So everybody understood. Okay, I'll repeat one more time and then you tell me whether you understood or not. Okay, so they have given this reaction to us. What reaction? PCl5 giving PCl3 plus Cl2 reaction to us. And what else they have told us? Vessel, right? And they told you that at equilibrium, 60% of reaction has been completed. And in the sense that 60% of PCl5 have been converted into products. Okay, now what you're going to do, you are going to make the equilibrium table. This is what is the equilibrium table, right? At time t is equal to 0, what is the data? At equilibrium, what is the data? That is it. For all the reactants and products you are going to fill. That is what is equilibrium table, right? So at time t is equal to 0, they say that I have 5 moles of PCl5 and obviously nothing of PCl3 and Cl2. Now what they say at equilibrium, like I'm just putting some X now. We'll fill the X, right? So some X would have reacted. Out of the 5 moles, some X would have reacted and whatever has reacted would have come here, right? So from the stoichiometry, you can see that 1 mole of PCl5 gives 1 mole of PCl3 and 1 mole of Cl2. So if X moles are reacting, X moles here and X moles here. Now from the data from the question, I'll be able to find what is this X value. They tell that 60% of PCl5 is converted, right? That means out of this 5, 60% of them have been converted to products. Okay, so basically so basically how much of PCl5 is reacting? 60% of 5 is only reacting. So basically this X is basically going to be 60% of 5 and 60% of 5 is 3. And how much is reacting here will come here. That is 3 moles here, 3 moles here, and that's it. You can find these are the number of moles at equilibrium. You can find the concentrations at equilibrium, that is the number of moles by volume. Then you can find the Kc value, right? Everybody understood? I want everybody to give me an S.
Understood, sir, but I have a small doubt.
Yeah.
What unit should we put, sir? Like 4.5 what?
1 second. Let me do that. Right. So what you see here is that you have this is a concentration. This is also concentration. This is also concentration. Correct? Right. So can I say one concentration term, other concentration term will get cancelled? This is mole per liter. Another mole per liter will get cancelled. So what is remaining here? Only 1 mole per liter. So here the answer is 4.5 mole per liter. So it depends. For this question, you're getting like this mole per liter, but it depends on the powers on the numerator and depends on the powers on the denominator, right? So whatever you have, say product power n and say reactant power m, if you have, so this is basically mole per liter power n minus m, will come. If you're really interested in the units, are you able to understand what I'm telling?
Yes, sir. Understood.
Right?
Sir.
So it depends on the question, depends on the stoichiometric coefficients. What they have, according to the unit will change for every question, every reaction for that matter. Okay, so yeah, so I want everybody to give me a yes. Everybody understood? There's one chat.
Yes, sir. Understood.
Bhavadarani says, yes, sir, the audio is stopping for me suddenly. I have to rejoin again and again. Kindly excuse if I leave the meet. Okay, no issues, Bhavadarani. Okay, so yeah, so I want everybody, yes, Vanisha says yes.
Yes, sir, understood.
Okay, 3.
Yes, sir.
4. Okay, 5. 6. Okay, fine. So I hope everybody understood, right? So now we will do some other example. Let me take another example. Okay, say now I take this reaction. Now I have, say, N2 plus 3H2 giving 2 NH3. Okay, right? Fine. So now say assume that they have given initially, right? So let me write it here, maybe. Okay, so say the question is initially say they have given me say 2 moles of N2, right, and say 3 moles of H2, right, and say the Kc value is given to be some, say 3 into 10 to the power minus 3 is what is given. Kc value is given. Okay, now they're asking you at equilibrium, what is the number of moles of all of them? Number of moles of N2, or let's say you can even find the concentration. If I give you the volume, say assume that the volume is 1 liter. Volume of the vessel is 1 liter. Okay, right? So obviously I wanted to find what are the equilibrium concentrations of all the things. That is your N2, H2 and NH3. Okay, I wanted to find at equilibrium what are all the concentrations. This is the question. Okay, now this is like opposite of what we saw last class. I mean last question, right? Now last time I gave you basically indirectly I gave you what are the concentrations at equilibrium, and then I asked you to find what is the Kc value. Now they have given the Kc value, and they're asking us to find the number of moles or say the concentrations of all these 3 species at equilibrium. Okay, so again, you are going to make sure that you're going to do the equilibrium table very, very, very properly. And if you do that, 90% of job is done there only, as I told you, right? Say at time t is equal to 0, right? So what they're given initially, initial number of moles of N2 is 2, right? Number of moles of H2 is 3, and there is no ammonia, so 0. Okay, right? So this is 2. Okay, so next at equilibrium. Right, so I don't know nothing. I don't know how much is reacting, so I'll just use my X. Okay, but you are going to help me now. Now tell me what should come here in place of N2. Say assume that some X mole, you can assume anything actually, some X moles of N2 is reacting, right? So what will I write here? If
2
X
minus
moles
X, sir.
Okay, so I write 2 minus X, absolutely true. Okay, now what should be for H2?
3 minus X.
No, that's not we should not do. Now that you have fixed X moles of N2 is reacting, now look at the stoichiometry, right? For 1 mole of N2, if it reacts, I require 3 moles of H2 and I form 2 moles of ammonia. So now what should I write here? Think and tell me. For H2. 1 mole of N2 reacting, I require 3 moles. Now, how many moles of N2 is reacting and how many? So, what should come here? Think
6
like
minus 3x, sir.
Come again?
6 minus 3x.
Why 6 minus 3x? Initially, how many moles of H2 I have? Only 3. So 3 minus, how much reacting? For 1 mole of N2 requires 3 moles. So if I have X moles, how many moles of H2 is required? 3x. Everybody understood how 3 minus 3x came, right? Say, you don't have to worry about this number. This number comes from initially. That doesn't matter at all, right? What matters is, now that you have said me that X moles of N2 is reacting, now if you look at the stoichiometry, 1 mole of N2 requires 3 moles of H2, right? So now I have 3 moles of, okay, so I have X moles of N2 H2 reacting. So definitely I will be requiring 3x moles of H2 to be reacting, right? So now what is this 3 minus 3x? 3 minus 3x is the remaining number of moles after the reaction is completed. Okay, so again, did you understand, everybody, how is it 3 minus 3x? Yes or no?
Yes, understood.
Okay, cool, right? So this is 3. Okay, now what should come here for now for ammonia? For ammonia, what should come here? Same thing, right? I have
2x.
tell
Sir.
me. That's it. That's it. Very simple. I have 1 mole of N2 giving 2 moles of ammonia. Now, how much is reacting? X moles of N2 is reacting. So I should be getting 2x moles of ammonia. That's it. And obviously the concentrations are going to be same. 2x, 2 minus x divided by 1, this divided by 1, this divided by 1, because the volume is 1 liter, right? What is the time? Okay, we have time. The volume is 1 liter. Now what I have to find? Basically, I have to find these values. I have to find this entire value. I have to find this entire value. I have to find this entire value, because that is what is asked question. You can see that what are the concentrations of all these 3 species at equilibrium, right? At equilibrium, what are all the concentrations? And for that, what I have to do? Though you have given me Kc value, now you can substitute all these things in the Kc value. Okay, now you are going to tell me how am I going to fill it. Now tell me Kc will be equal to what? Tell me, how will I write? Numerator, what should come?
2x, sir.
That's it, nothing else. Nothing at the powers. These are the equilibrium concentration. So if I write concentration of ammonia, is that it? Anything else should come?
Raised to the power 2, sir.
Correct, right? So this should be concentration of ammonia squared, obviously, because I have a stoichiometric coefficient of 2, right? So obviously now I'll drop it off. Now tell me what should come in numerator.
2x raised to the power 2.
Exactly, right? So it's 2x power 2, right? Okay, denominator.
2 minus x into 3 minus 3x raised to the power 3.
Exactly, right? 2 minus x for this N2 power 1 only. And for H2, it is 3 minus 3x. But I have 3H2, that is 3 as a stoichiometric coefficient. So this would be 3. And the Kc value we know. Kc value is 3 into 10 to the power minus 3. And you can find the x value now, obviously, right? You can, if you can expand and you can find the x values and substitute it here. Answer is the answer for this question would be 2 minus x, 3 minus 3x, and 2x. If you find the x value from this equation, right? From this equation, you can substitute the x values here in these 3, and you can find the equilibrium concentrations. Okay, right? Fine. And everybody understood how all these things are done now? Right, we'll take one more example. One more example we'll take. Right, let me think of a reaction. Okay, I think now we can take the HI's example, right? Say I have H2 plus I2 giving, or let me, okay, fine, no issues. To HI, right? Now, 1 second, guys. Okay, right. Say now, how can I ask the question? Now I can ask the question. Okay, now let me put it like this. I had I had say 2 moles initially, 2 moles of H2 and I2 each, right? 2 moles of H2 and I2 each, and say it's a 2-liter vessel, right? It's a 2-liter vessel, okay? And what can I say? What can I tell? Right. So I can say that at equilibrium, mm, concentration of HI is equal to concentration of H2, and that is equal to concentration of I2. Okay, so this data is given to you, right? Say I want to find what is the Kc value. Can I find it? Is it possible? Okay, we'll try. I don't know whether the question works or not, but still we'll try. Right? So these are the informations given to you. So they're given that 2 moles each of H2 and I2 are present, right? And it's a 2-liter vessel. So they say that at equilibrium, all the concentrations are equal. Okay, and I want to find what is the Kc value. Right. Okay. Now again, I'll go for the equilibrium table. Right, I'll go for the equilibrium table, that is at time t is equal to 0. Right. Okay. Right. So at time t is equal to 0, right? So basically they say that I had 2 moles of this and 2 moles of this and 0 moles of this. Okay, right. Now tell me at equilibrium. Now tell me, how will I fill this quickly? H2. What
2
will I do?
minus x.
Okay, 2 minus x. Then I2.
2 minus x. Yeah.
Again 2 minus x, because now the initial number of moles are same, so you're putting 2 and 2 here, and obviously 1 mole of H2 requires 1 mole of I2, so x and x. Okay, for HI
2x. Yeah.
exactly 2x. So 1 mole of H2 gives me 2 moles of HI, so here it should be 2x. Now these are the number of moles, right? Now I have to, if I do it in terms of concentration, okay, so this concentration at equilibrium, it will be what? 2 minus x divided by 2, this divided by 2, and 2x divided by 2. Okay, now what they are telling? They are telling that the concentration of HI at equilibrium is equal to any of the two concentrations of H2 or I2. Okay, so now how will I go about the question? Now I can take this, so 2 and 2 gets cancelled, so I can write x is equal to, now what I have, I can take either one of them, say so it will be 2 minus x divided by 2. So now how can I write this? So this will be 2x is equal to 2 minus x, and if I bring this x this side, so x becomes 2. Is it? Am I doing something wrong?
It will be 3x equal to 2, sir.
Oh, yeah, correct. If it becomes a plus, so x will become 2 by 3, right? So this will be, yeah. So if this x comes here, it will become 3x equal to 2. So x will become equal to 2 by 3. And that's it. Now what do you have to do? You have to substitute everything here. Okay, find 2 minus x by 2, again 2 minus x by 2. You have to find a just x value and then go to the Kc equation. Kc equation would be what? Kc equation hi squared divided by H2's concentration into I2's concentration, and everything you know, because you know the x value, you know x here, you know 2 minus x by 2, you know 2 minus x by 2. Substitute it here, you will be able to get the Kc value. Yes, everybody understood. Now, any type of question given to you, as I told you, if you can make this alone very properly, the equilibrium table, rest all the things, Kc, obviously you have to know the formula. If you know the formula and if you do the equilibrium table properly, any problem can be solved in just in minutes. Okay, now I can complicate it a little bit more if I can include Kp, and obviously I can include the partial pressures. I know partial pressures and mole fractions are little connected. So all these things again, I can little I can improve the difficulty level. That we'll see maybe in the tomorrow's class. What is the time? So yeah, almost it's time, right? So that maybe we'll see in tomorrow's class. Okay, and we'll solve some more questions. I'll give you some time to for you to solve some questions, right? So if I complete this, like as I told you, this is like equilibrium and ionic equilibrium together. So equilibrium, after I complete, if you know how to solve the problems, then going for ionic equilibrium is pretty easy. Okay, right? So any questions, people? Any questions from anywhere from what we saw? Okay, and be ready tomorrow. Okay, I'll ask you individual persons, individual steps, what comes here, what comes there, then what you have to do. Please be very careful. That is how we're going to solve the problem.
So we have
Okay.
class, sir.
Not tomorrow, next class, Monday.
Okay.
But I think we missed one class, isn't it? We missed class on Monday, right? Guys, is it okay for you to have maybe tomorrow? Can we have a class? Is it okay for you? Yes, no. Max exam is on Monday. Okay. Children, so if that's the case, maybe fine. Okay, we'll see what we can do. Okay, so now you said that you have exam, right? Fine. Okay, no issues. Maybe we'll compensate it some other day. Okay. So any other questions, people, regarding equilibrium or any other chapter? Okay, I hope there are no questions, right? So yeah.
Sir, I have a doubt in redox reaction regarding that balancing.
Yeah, you can ask.
Yesterday I saw the video, sir.
Okay.
But then I understood the half reaction, reaction method. But I was not able to understand that oxidation number method, sir.
Kana oxidation number method, I would like in the school, are they asking you to solve specifically by one method only? Are they asking you like that?
If they specify, we have to solve like that. They might specify.
Definitely.
That's the oxidation reaction.
Yeah, that is true. If they specifically ask you, yes, you have to do it. But but preferably, if they don't specify anything, please go for half reaction method, because that is always easier. Okay, but now I can explain you. We'll just take a small example, and then maybe I'll explain you how to do it. Right? Yeah. So let me take something like this. I have, say, Mn2 plus or Mn. Okay, MnO4 minus. Sorry. Right. Say I take MnO4 minus plus, say I take Fe2 plus. This is an oxidizing agent, KMnO4, so it will oxidize Fe2 plus to Fe3 plus. Right, and assume that this is going to happen in acidic medium, I just give H plus, meaning that it is going to be an acidic medium. So the acidic medium MnO4 minus becomes Mn2 plus. Okay, right? Fine. So now we are going to solve this by oxidation number method. Okay, now you can easily find what is the oxidation number of manganese here. It is 7 plus 7 here, and for Fe it is plus 2, and here it is plus 3, and here it is plus 2. Right? Okay. Now you're going to see which is getting reduced and which is getting oxidized. Now you can see here that 7, that is the oxidation number. Whenever it's reducing, it's reduction, right? So number of electrons gained is 5 electrons. Done, right? And 5 electron, obviously this is reduction. You can even mention it here. 5 electrons reduction, right? Electrons you can mention. Okay, now if I go for Fe2 plus and Fe3 plus, you can see that there is increase in oxidation number, right? Increase in oxidation number is oxidation, and how many electrons? Only one electron, right? And obviously this is oxidation. Okay, now what is the next step? Next step would be to making sure that the number of electrons lost and number of electrons gained are equal, right? So what I have to do now, this is 5, this is 1. So obviously the best way to do it is multiply this by 5, right? So if I multiply this by 5, I'll put 5 here and 5 here. And next, what is the change? I have to go for charge balance, right? So charge balance, you can see I have -1 here, and I have 5 into plus 2 will become, sorry, 5 into 2 is still a 10, and 10 minus 1 will become plus 9. And here if I go, here it is 5 into 3 is 15, 15 plus 2 will become 17, plus 17 is what I have here, right? So I have to make sure that the charge on reactant side and the charge on product side is going to be, should be same. So, and they have given me that they have to add H plus only. So definitely I have to add H plus in the reactant side. So H plus in the reactant side will become, so I have to basically add 8 H plus, right? So I can just add 8 H plus. And obviously you have to make sure that the water molecule is also, the hydrogen atom is getting compensated in terms of water. So I have 8 H plus. So I can put in the product side 4 H2O. Yeah, this is how you do it with the help of oxidation number method. See, the last step, the charge balance step is exactly same, whether it's going to be oxidation number method or whether it's going to be half reaction method. The second step, that is the charge balance, H plus OH minus H2O, those things are same. Only part will be different is this part. When you just multiply by a factor and all these things you do, only that part will be different. Okay, yeah, understood?
Yes, sir, understood, sir.
Right, if you solve more questions, right? But what you have to be very, very careful is when I have Cr2O7 and all, right? Now you have to be very, very careful with this too, because now you will have reactant side, you will have 2, and the product side, you will have only 1. So you have to now, if you're going to use this method, half reaction, oxidation number method, you have now say, if you look at this, this will be +6, this will be +3, right? So you just say that 3 electrons are going, but no, it should be 6 electrons for one formula unit. For 1 chromium, it is 3. For 2 chromium, it is 6. So accordingly, you have to do it. And you have to directly put a 2 here, and all these things has to happen. So yeah, it's pretty complicated when I go for oxidation number method. So I always prefer half reaction method. But if they specifically ask you, then you don't have a choice. Please go for this. But this is also easy only. Okay.
Okay, sir. Thank you, sir.
Right. Yeah. Thank you, guys. Any other questions, people? Okay.
No, sir.
Right. Okay. Thank you, guys. You can go and go take some rest, attend your school classes. We'll end this. Thank you so much.
Thank you, sir.
Yeah.